Artificial intelligence, or AI for short, is a combination of computer science, physiology, and philosophy. AI is a broad topic consisting of different fields, from machine vision to expert systems. The element that the fields of AI have in common is the creation of machines that can think. In order to classify machines as thinking, it is necessary to define intelligence. To what degree does intelligence consist of, for example, solving complex problems, or making research into the areas of learning, of language, and of sensory perception have aided scientists in building intelligent machines. One of the most challenging approaches facing experts is building systems that mimic the behavior of the human brain, made up of billions of neurons, and arguably the most complex matter in the universe. Perhaps the best way to gauge the intelligence of a machine is British computer scientist Alan Turing's test. He stated that a computer would deserve to be called intelligent if it could deceive a human into believing that it was human. Artificial intelligence has come a long way from its early roots, driven by dedicated researchers. The beginnings of AI reach back before electronics, to philosophers and mathematicians such as Boole and others theorizing on principles that were used as the foundation of AI logic. AI really began to intrigue researchers with the invention of the computer in 1943. The technology was finally available, or so it seemed, to simulate intelligent behavior. Over the next 4 decades, despite many stumbling blocks, AI has grown from a dozen researchers to thousands of engineers and specialists, and from programs capable of playing checkers to systems designed to diagnose disease. AI has always been on the pioneering end of computer science. Advanced-level computer languages, as well as computer interfaces and word processors, owe their existence to the research into artificial intelligence. The theory and insights brought about by AI research will set the trend in the future of computing. The products available today are only bits and pieces of what are soon to follow, but they are a movement towards the future of artificial intelligence. The advancements in the quest for artificial intelligence have and will continue to affect our jobs, our education, and our lives. Game playing. You can buy machines that can play master-level chess for a few $100s. There is some AI in them, but they play well against people mainly through brute force computation, looking at hundreds of thousands of positions. To beat a world champion by brute force and known reliable heuristics requires being able to look at 200 million positions per second. Speech recognition. In the 1990s, computer speech recognition reached a practical level for limited purposes. Thus, United Airlines has replaced its keyboard tree for flight information by a system using speech recognition of flight numbers and city names. It is quite convenient. On the other hand, while it is possible to instruct some computers using speech, most users have gone back to the keyboard and the mouse as still more convenient. Computer vision. The world is composed of three-dimensional objects, but the inputs to the human eye and computer's DV cameras are two-dimensional. Some useful programs can work solely in 2 dimensions, but full computer vision requires partial 3-dimensional information that is not just a set of 2-dimensional views. At present, there are only limited ways of representing 3-dimensional information directly, and they are not as good as what humans evidently use. Expert systems. A knowledge engineer interviews experts in a certain domain and tries to embody their knowledge in a computer program for carrying out some task. How well this works depends on whether the intellectual mechanisms required for the task are within the present state of AI. When this turned out not to be so, there were many disappointing results. One of the first expert systems was Mycin in 1974, which diagnosed bacterial infections of the blood and suggested treatments. It did better than medical students or practicing doctors, provided its limitations were observed. Namely, its ontology included bacteria, symptoms, and treatments, and did not include patients, doctors, hospitals, death, recovery, and events occurring in time. Its interactions depended on a single patient being considered. Since the experts consulted by the knowledge engineers knew about patients, doctors, death, recovery, etc., it is clear that the knowledge engineers forced what the experts told them into a predetermined framework. In the present state of AI, this has to be true. The usefulness of current expert systems depends on their users having common sense. Heuristic classification. One of the most feasible kinds of expert system given the present knowledge of AI is to put some information in one of a fixed set of categories using several sources of information. An example is advising whether to accept a proposed credit card purchase. Information is available about the owner of the credit card, his record of payment, and also about the item he is buying, and about the establishment from which he is buying it, e.g., about whether there have been previous credit card frauds at this establishment. Understanding natural language. Just getting a sequence of words into a computer is not enough. Parsing sentences is not enough either. The computer has to be provided with an understanding of the domain the text is about, and this is presently possible only for very limited domains. What are the branches of AI? Here's a list, but some branches are surely missing, because no one has identified them yet. Some of these may be regarded as concepts or topics rather than full branches. Logical AI. What a program knows about the world in general, the facts of the specific situation in which it must act, and its goals are all represented by sentences of some mathematical logical language. The program decides what to do by inferring that certain actions are appropriate for achieving its goals. The first article proposing this was MCC 59. MCC 89 is a more recent summary. MCC 96 lists some of the concepts involved in logical AI. SHA 97 is an important text. Search. AI programs often examine large numbers of possibilities, e.g. moves in a chess game or inferences by a theorem-proving program. Discoveries are continually made about how to do this more efficiently in various domains. Pattern recognition. When a program makes observations of some kind, it is often programmed to compare what it sees with a pattern. For example, a vision program may try to match a pattern of eyes and a nose in a scene in order to find a face. More complex patterns, e.g. in a natural language text, in a chess position, or in the history of some event are also studied. These more complex patterns require quite different methods than do the simple patterns that have been studied the most. Representation. Facts about the world have to be represented in some way. Usually languages of mathematical logic are used. Inference. From some facts, others can be inferred. Mathematical logical deduction is adequate for some purposes, but new methods of non-monotonic inference have been added to logic since the 1970s. The simplest kind of non-monotonic reasoning is default reasoning, in which a conclusion is to be inferred by default, but the conclusion can be withdrawn if there is evidence to the contrary. For example, when we hear of a bird, we may infer that it can fly, but this conclusion can be reversed when we hear that it is a penguin. It is the possibility that a conclusion may have to be withdrawn that constitutes the non-monotonic character of the reasoning. Ordinary logical reasoning is monotonic in that the set of conclusions that can be drawn from a set of premises is a monotonic increasing function of the premises. Common sense knowledge and reasoning. This is the area in which AI is farthest from human level, in spite of the fact that it has been an active research area since the 1950s. While there has been considerable progress, e.g., in developing systems of non-monotonic reasoning and theories of action, yet more new ideas are needed. The KIC system contains a large but spotty collection of common sense facts. Learning from experience. Programs do that. The approach is theory-based and connectionism, and neural nets specialize in that. There is also learning of laws expressed in logic. MIT 97 is a comprehensive undergraduate text on machine learning. Programs can only learn what facts or behaviors their formalisms can represent, and unfortunately learning systems are almost all based on very limited abilities to represent information. Planning. Planning programs start with general facts about the world, especially facts about the effects of actions, facts about the particular situation, and a statement of a goal. From these, they generate a strategy for achieving the goal. In the most common cases, the strategy is just a sequence of actions. Epistemology. This is a study of the kinds of knowledge that are required for solving problems in the world. Ontology. Ontology is the study of the kinds of things that exist. In AI, the programs and sentences deal with various kinds of objects, and we study what these kinds are and what their basic properties are. Emphasis on ontology begins in the 1990s. Heuristics. A heuristic is a way of trying to discover something, or an idea embedded in a program. The term is used variously in AI. Heuristic functions are used in some approaches to search to measure how far a node in a search tree seems to be from a goal. Heuristic predicates that compare two nodes in a search tree to see if one is better than the other, i.e. constitutes an advance toward the goal, may be more useful. My opinion. Genetic programming. Genetic programming is a technique for getting programs to solve a task by mating random Lisp programs and selecting fittest in millions of generations. It is being developed by John Koza's group, and here's a tutorial. What are artificial neural networks? A neural network is an interconnected assembly of simple processing elements, units, or nodes, whose functionality is loosely based on the animal neuron. The processing ability of the network is stored in the inter-unit connection strengths, or weights, obtained by a process of adaptation to, or learning from, a set of training patterns. Artificial neural networks are relatively crude electronic models based on the neural structure of the brain. The brain basically learns from experience. It is natural proof that some problems that are beyond the scope of current computers are indeed solvable by small energy-efficient packages. This brain modeling also promises a less technical way to develop machine solutions. This new approach to computing also provides a more graceful degradation during system overload than its more traditional counterparts. These biologically inspired methods of computing are thought to be the next major advancement in the computing industry. Even simple animal brains are capable of functions that are currently impossible for computers. Computers do rote things well, like keeping ledgers or performing complex math. But computers have trouble recognizing even simple patterns, much less generalizing those patterns of the past into actions of the future. Now, advances in biological research promise an initial understanding of the natural thinking mechanism. This research shows that brains store information as patterns. Some of these patterns are very complicated and allow us the ability to recognize individual faces from many different angles. This process of storing information as patterns, utilizing those patterns, and then solving problems is a new field in computing. This field, as mentioned before, does not utilize traditional programming, but involves the creation of massively parallel networks and the training of those networks to solve specific problems. This field also utilizes words very different from traditional computing, words like behave, react, self-organize, learn, generalize, and forget. Analogy to the brain. The exact workings of the human brain are still a mystery. Yet, some aspects of this amazing processor are known. In particular, the most basic element of the human brain is a specific type of cell which, unlike the rest of the body, doesn't appear to regenerate. Because this type of cell is the only part of the body that isn't slowly replaced, it is assumed that these cells are what provides us with our abilities to remember, think, and apply previous experiences to our every action. These cells, all 100 billion of them, are known as neurons. Each of these neurons can connect with up to 200,000 other neurons, although 1,000 to 10,000 is typical. The power of the human mind comes from the sheer numbers of these basic components and the multiple connections between them. It also comes from genetic programming and learning. The individual neurons are complicated. They have a myriad of parts, subsystems, and control mechanisms. They convey information via a host of electrochemical pathways. There are over 100 different classes of neurons, depending on the classification method used. Together these neurons and their connections form a process which is not binary, not stable, and not synchronous. In short, it is nothing like the currently available electronic computers, or even artificial neural networks. These artificial neural networks try to replicate only the most basic elements of this complicated, versatile, and powerful organism. They do it in a primitive way. But for the software engineer who is trying to solve problems, neural computing was never about replicating human brains. It is about machines and a new way to solve problems. Artificial neurons and how they work. The fundamental processing element of a neural network is a neuron. This building block of human awareness encompasses a few general capabilities. Basically, a biological neuron receives inputs from other sources, combines them in some way, performs a generally nonlinear operation on the result, and then outputs the final result. Figure shows the relationship of these four parts. Within humans there are many variations on this basic type of neuron, further complicating man's attempts at electrically replicating the process of thinking. Yet, all natural neurons have the same four basic components. These components are known by their biological names: dendrites, soma, axon, and synapses. Dendrites are hair-like extensions of the soma which act like input channels. These input channels receive their input through the synapses of other neurons. The soma then processes these incoming signals over time. The soma then turns that processed value into an output which is sent out to other neurons through the axon and the synapses. Recent experimental data has provided further evidence that biological neurons are structurally more complex than the simplistic explanation above. They are significantly more complex than the existing artificial neurons that are built into today's artificial neural networks. As biology provides a better understanding of neurons, and as technology advances, network designers can continue to improve their systems by building upon man's understanding of the biological brain. But currently, the goal of artificial neural networks is not the grandiose recreation of the brain. On the contrary, neural network researchers are seeking an understanding of nature's capabilities for which people can engineer solutions to problems that have not been solved by traditional computing. To do this, the basic unit of neural networks, the artificial neurons, simulate the four basic functions of natural neurons. Figure shows a fundamental representation of an artificial neuron. Electronic implementation of artificial neurons. In currently available software packages, these artificial neurons are called processing elements and have many more capabilities than the simple artificial neuron described above. Those capabilities will be discussed later in this report. Figure is a more detailed schematic of this still simplistic artificial neuron. Inputs enter into the processing element from the upper left. The first step is for each of these inputs to be multiplied by their respective weighting factor, Wn. Then these modified inputs are fed into the summing function, which usually just sums these products. Yet, many different types of operations can be selected. These operations could produce a number of different values which are then propagated forward, values such as the average, the largest, the smallest, the ORed values, the ANDed values, etc. Furthermore, most commercial development projects allow software engineers to create their own summing functions via routines coded in a higher level language. C is commonly supported. Sometimes the summing function is further complicated by the addition of an activation function which enables the summing function to operate in a time-sensitive way. Either way, the output of the summing function is then sent into a transfer function. This function then turns this number into a real output via some algorithm. It is this algorithm that takes the input and turns it into a 0, or 1, a -1, or 1, or some other number. The transfer functions that are commonly supported are sigmoid, sine, hyperbolic tangent, etc. This transfer function also can scale the output or control its value via thresholds. The result of the transfer function is usually the direct output of the processing element. An example of how a transfer function works is shown in figure. This sigmoid transfer function takes the value from the summation function, called sum, in the figure, and turns it into a value between 0 and 1. Artificial network operations. The other part of the art of using neural networks revolve around the myriad of ways these individual neurons can be clustered together. This clustering occurs in the human mind in such a way that information can be processed in a dynamic, interactive, and self-organizing way. Biologically, neural networks are constructed in a three-dimensional world from microscopic components. These neurons seem capable of nearly unrestricted interconnections. That is not true of any proposed or existing man-made network. Integrated circuits, using current technology, are two-dimensional devices with a limited number of layers for interconnection. This physical reality restrains the types and scope of artificial neural networks that can be implemented in silicon. Currently, neural networks are the simple clustering of the primitive artificial neurons. This clustering occurs by creating layers which are then connected to one another. How these layers connect is the other part of the art of engineering networks to resolve real-world problems. Basically, all artificial neural networks have a similar structure or topology, as shown in Figure 2.4.1. In that structure, some of the neurons interfaces to the real world to receive its inputs. Other neurons provide the real world with the network's outputs. This output might be the particular character that the network thinks that it has scanned, or the particular image it thinks is being viewed. All the rest of the neurons are hidden from view. But a neural network is more than a bunch of neurons. Some early researchers tried to simply connect neurons in a random manner, without much success. Now, it is known that even the brains of snails are structured devices. One of the easiest ways to design a structure is to create layers of elements. It is the grouping of these neurons into layers, the connections between these layers, and the summation and transfer functions that comprises a functioning neural network. The general terms used to describe these characteristics are common to all networks. Although there are useful networks which contain only one layer, or even one element, most applications require networks that contain at least the three normal types of layers: input, hidden, and output. The layer of input neurons receive the data either from input files or directly from electronic sensors in real-time applications. The output layer sends information directly to the outside world, to a secondary computer process, or to other devices such as a mechanical control system. Between these two layers can be many hidden layers. These internal layers contain many of the neurons in various interconnected structures. The inputs and outputs of each of these hidden neurons simply go to other neurons. In most networks, each neuron in a hidden layer receives the signals from all of the neurons in layer above it, typically an input layer. After a neuron performs its function, it passes its output to all of the neurons in the layer below it, providing a feed-forward path to the output. Note: in section 5 the drawings are reversed. Inputs come into the bottom and outputs come out the top. These lines of communication from one neuron to another are important aspects of neural networks. They are the glue to the system. They are the connections which provide a variable strength to an input. There are two types of these connections. One causes the summing mechanism of the next neuron to add, while the other causes it to subtract. In more human terms, one excites while the other inhibits. Some networks want a neuron to inhibit the other neurons in the same layer. This is called lateral inhibition. The most common use of this is in the output layer. For example, in text recognition, if the probability of a character being a P is 0.85 and the probability of the character being an F is 0.65, the network wants to choose the highest probability and inhibit all the others. It can do that with lateral inhibition. This concept is also called competition. Another type of connection is feedback. This is where the output of one layer routes back to a previous layer. An example of this is shown in figure. The way that the neurons are connected to each other has a significant impact on the operation of the network. In the larger, more professional software development packages, the user is allowed to add, delete, and control these connections at will. By tweaking parameters, these connections can be made to either excite or inhibit